All right, class. This is HIP528 week 5. As I was thinking about what to do in this video lecture, I thought to keep it simple and short. So my goal for this lecture, is to uh, give you all the tools necessary to run any sort of linear regression, simple linear regression. So we'll finalize simple linear regression so that way when we see each other next time in 2 weeks, you'll know exactly how to interpret these things, how to interpret these linear regression models, how to do some validation checks, and we'll talk a little bit about another sort of model diagnostic called leverage. So I think that's my goal for this video, is to help you sort of tie everything together so that when we move to multiple linear regression, it won't catch you off guard, because at that point when you're adding more variables, it can get complicated pretty fast. So again, we'll keep it short, and we'll talk about a couple extra additional things, and then sort of have you be experts at simple linear regression. So we'll begin here. We'll continue using the fish data set, and so last time we discussed that there may be some sort of connection here between pregnancy and fish intake, and so we have data for 341 mother-child pairs. And again, the goal was to study the evaluation or the association between fish intake, mercury levels, and children's score and cognitive functioning tests. So we considered several different types of examples. We said, what's the impact of breastfeeding in months on child's intelligence? What's the impact of mom's intelligence on child's intelligence? And so we had these sort of questions that where you had a continuous outcome, and you had some sort of either continuous predictor or a binary predictor. And so let's just take, for example, the case where you had child PPVT, the continuous outcome, and then you had mom PPVT, a continuous predictor. So you could potentially think about doing a scatter plot, right? So you could scatter child PPVT on mom PPVT, and then you get some sort of relationship there. And so we know that we said, well, we could analyze this through either a Pearson correlation or a Spearman correlation, but it would be really nice to say something meaningful of like, how does an increase in mother's intelligence impact a child's intelligence? And so we said one of the best ways to represent that is through the simple idea of a line, right? So a linear regression is essentially that an attempt to try to fit a line through these data points. And so we said there's an infinite number of ways to do that. So how do we figure out the best way? And so we made a few assumptions. We said, if you can assume normality, if you can assume linearity, if you can assume homoscedasticity and independence, so assume these things, what's the best way to describe the relationship between x and y? And so we said it's through a line, and then specifically through the method of least squares. So there's some sort of true population regression line where you're modeling the mean of y for every value of x as a function of some sort of intercept, a y-intercept, and then a slope, right? So a beta, and that's what this beta is doing. And again, this is in the population. You take a sample, and from your sample, you can estimate the least square line. So these alpha hat is the best estimator for this alpha, and beta hat is the best estimator for beta. And the way that any of these, the way that least squares or simple linear regression estimates these numbers is by considering residual. So how far away is each data point from the least squares line, and then so you're trying to minimize that distance. And so we talked about that last time. And so this method of least squares is essentially a operationally trying to minimize that distance between the line and the observed values. Okay, so we said then let's consider an example where you're interested in the regression of child PPVT scores on mom PPVT scores, and so that is this linear regression. So we'll close this, and we said, well, let's get a regression of child PPVT scores on mom PPVT scores. And you get this relationship. So we said last time, there's a few statistics here, but this coefficient here is beta hat. So this is the slope of a linear regression of child PPVT and mom PPVT. And then this coefficient is alpha hat. And so we said again last time, we interpreted this as this is the mean child PPVT score for mothers who scored a value of 0, which in this case doesn't make sense. But this actually does make sense, and this is the beta coefficient for mom PPVT. This is saying that for every increase, 1 unit increase in mom score, the average child score goes up by 0.35. And this is statistically significant, and we can talk about other things in a bit, but first I wanted to sort of stop here and show you a nice little way to visualize this. So occasionally it's really nice, as we said earlier, it's really nice to look at the scatter plot. So we've done that, but there's a way in Stata where you can actually produce a scatter plot for two continuous variables and then draw a line, the least squares line. So you can imagine that if you had a y-intercept of 67.4 and a slope of 0.35, you can draw a line in that figure. And so to do that in Stata, you can do that using the graph2way command, where you're essentially plotting two different types of plots in one graph. So the first is this L-fit. So that's that linear fit using linear regression of child PPVT and mom PPVT. So this will be the first plot, and then the second plot would be the scatter plot of interest. So child PPVT and mom PPVT. So the same variables. So again, outcome, predictor, y-axis, x-axis. If you type that in, you get this figure. So again, it's the exact same figures we saw before, and what it does is just adds fitted values line, so it adds this least squares regression line. So visually it tells you that there's a positive increase, and this slope is 0.35. Yeah, so this is a really nice way to visualize your data in case you're interested. So we'll put that away for now. So we have that. We talked about interpretation, and then we said, well, okay. So there's clearly a relationship here based on the p-value, and this effect seems pretty large, or at least 0.35. But how well does this model fit the observed data, right? So we don't want to just stop here and report this. We also want to just make sure that the model we have is a good model that can describe the observed data. And we talked about 3 different ways to do this. We talked about the coefficient of determination, residual versus fitted plot, and then a residual plot. So just to recap, the coefficient of determination is the proportion of total observed variability among the y values that is explained by this linear regression. So if we go back here to this regression, that's represented here, and so that r squared is about about 14% of the variability in children's intelligence is being explained by this regression model that includes mom intelligence. So that's it's a pretty good number, but it's still in the lower end of the range. So remember, 0 indicates a poor fit, low prediction. Value of 1 indicates high prediction, perfect fit. So again, an indication of 13% variability suggests that there's probably other factors that explain child's intelligence. So we're gonna in the future go through and try to figure out what those are. But this is just one statistic that'll help us determine or gives us a sense of how well this model is at being predictive. And then we said was then there's some other assumptions. So coefficient of determination gets at sort of the predictive ability of this model, but it still doesn't tell us anything about the underlying assumptions of normality, linearity, homoscedasticity, and independence. So to actually assess those assumptions, we can look at these residual versus fitted plots, that they can help us do a few things. So it helps us determine the assumptions of homoscedasticity and linearity, but it also helps us to detect outliers. And this is something we touched a little bit upon, but this is something I want to go through now with this new idea of leverage. So there's a new statistic I'm going to introduce you to, but the idea here is, if you see a potential outlier through these residual versus fitted plots, then you have to figure out a way to sort of identify, is this a really is this outlier causing a lot of issues? Because the method of least squares is very sensitive to outliers, right? So this line is trying to sort of balance the distance between this line and this point, and so you have, potentially this value here, that could be messing up a little bit of the sort of the true slopes, right? So that's the idea of that's potentially causing bias. And so how do we determine that this is, that this may be a problematic issue? So so that's what we'll talk about next. So let's actually do this here. So if we wanted to construct a two-way scatter plot, just for the sake, because I don't think we covered this example. So if you want to do a residual versus fitted plot, you first run your regression, and then you can type in RVF plot, and then it gives you the residual versus fitted plot. And again, what you want to see is a random scatter, almost like you took a shotgun to a wall, and we do see that, right? And so that's for homoscedasticity and for linearity as well. But we do see, again, this potential problem here. So it helps us identify outliers, and there may be this value that is causing issues. So that's the one thing I'm highlighting through as I see this. I see, for the most part, it looks pretty nonlinear. It looks like it's random scatter, though there is this one point here. I'm a little concerned about that, but we'll talk about a method to address how influential that is. And then we also said predict residuals are. So that's for this next part. So produce a histogram of the residuals. If they look normally distributed, then the assumption of normality holds. And so we said we could do that with the predict command. You use whatever variable you want to call it, comma r, and then you could do a histogram of the residuals and the normal. Okay, so again, looks pretty good. So for normality, looks really good. Again, there's also a few issues here. So again, for the most part, looks good. Okay. So now that you saw that figure, I think I want to now talk about. So you've gone through your regression model. You've said, I'm interested in mom PPVT scores impact on child score. You looked at the beta, you looked at the p-value, you looked at the r-squared. The r-squared wasn't that bad. You looked at the residual versus fitted plot. There was at one point normality seems pretty good, but there is that one point that could cause issues. So statisticians have developed statistics to identify influential points, and one of those statistics is something called leverage. And leverage, we're going to call it as H sub I. So this is H for every, so we're going to calculate some statistic called leverage for every patient I. And so the way we're defining leverage is it's a statistical measure of the potential ability of the ith subject. Again, we're going to calculate one for every subject to influence the regression parameter estimates. Okay, so a single data point outside the bulk of the data has an over proportional effect of impacting the regression line. So outliers have this issue to either pull away from or against the majority of the data, and can cause issues. So let's before we go through any of this, I want to go through a few examples of the different types of outliers. So not all outliers are the same. And so what I have here is a diagram of essentially three different types of outliers. So imagine that you have a data set where you have an y and you have an x, where the majority of the data points lies in a certain region, so just here. So you could potentially consider three different types of outliers. So you have an outlier A, you have an outlier B, and you have an outlier C. Okay, so one of the things that you can sort of represent is where does most of the bulk of y, so where do most of the x values take place? And so that's probably somewhere around here. Okay, so when I think of outliers, I think where are all the x values? Mostly around here. And where are all the y values? So the bulk of the y values are somewhere around here. And so if we're thinking about outliers, you could have a situation here where let's just imagine that you only have A right now. So ignore B and C. But suppose you have something like this where you have most of your data points here, and then you have an outlier in A here. So this is what we call an outlier in Y, because the bulk of the Y values are somewhere over here, and the bulk of the X values are somewhere over here. So this value A is within the majority of X range of X values, but it's outside the majority of Y values. Okay, so the question is does this kind of outlier cause any problems for the regression in terms of bias? And it turns out that these kind of outliers are not that problematic. So you can imagine, again, the method of least squares, what it's trying to do is trying to figure out a way to keep this line balanced across all points. So what an outlier in A may do, it may shift this line up a little bit, right? So it may actually be instead of here. So if you ignored this, let's say this is the line, and then you've introduced A, it may shift the line up. So you may get a little bit of bias in the y-intercept, but the slope should not be affected that much. So what we say is an outlier like A that's within the bulk of y, but outside the bulk, that is within the bulk of x, but is outside the bulk of y, is not too problematic in terms of bias for the slope. So which the slope again is sort of that number that tells you how does impacting x how does changing x impact y, right? So you're still getting a pretty close to unbiased estimator if you have an outlier like A in your analysis or in your data set. Okay, so now let's look at an outlier in B. So again, ignore right now that A and C exist, and suppose you only have this outlier B. So this outlier B is outside the bulk of X and outside the bulk of Y. But in this scenario, it's actually really close to this line here. So in this setting, when you have an outlier outside of the bulk of X and outside of the bulk of Y, but it's rather close to this regression line, it won't cause too much bias, right? Because it's still, if you sort of extend this line out, it's still really close to the regression line. So in this scenario, I would say that an outlier outside of the bulk of X and outside of the bulk of Y won't be problematic if it's close to this regression line. So this type of outlier doesn't really impact much, but this is something that I would still consider doing a sensitivity analysis and removing them, because you could potentially think of B here. If you move it out here, say out here, it's going to be outside the bulk of X and Y, and it may cause an inverse relationship, right? So if you have a B here, you may get a line that you're trying to fit this way. So again, outside the bulk of X and Y, problematic if it's sort of not, if it looks like it may be um, far away from the regression line. And so now let's consider the scenario here where you have C. So again, ignore A and B right now, but what if you have a outlier that is within the bulk of Y, so it's within that range, but it's outside the bulk of X, right? So it's outside the majority of X values. In this scenario, this is actually very problematic. So in this scenario where you have outside the bulk of X, but within the bulk of Y, these kind of outliers tend to pull the line down towards it. So you'll get a line probably that's a little more flat, and it may say that there is no relationship when reality there may be a relationship. Okay, so you have, imagine this slope here, it pulls it down because what this line is again trying to do, it's trying to sort of minimize that distance. This distance is pretty high here, so it tries to pull it down so that it's a little closer, but still sort of, you know, balanced among these points here. So so outside of Y, outside of X, but within Y is really problematic. Okay, and so how do we then identify what is problematic? And so that's the whole point of leverage, is it's a number that's trying to sort of figure out what's the influence of this point on this regression line, right? So you can imagine that A here doesn't affect them that much, and so we need to come up with a way to assign a low value to assign a low value here. So this value should denote how much impact or how much influence does it have. Um, again, so it's a measure of potential ability of the I subject to influence the regression parameter estimate. So what's the influence of this line, of this data point on the slope here? And so the same thing here. So again, since I described that this didn't really have a problem for the most part, we should assign a low value here. B may or may not, again, depending on where it's situated, may or may not have an impact. In this specific scenario, it likely will not have an impact, so we want to assign a low value here because it has low ability to actually change these regression estimates. C here can be problematic, and so for a statistic like leverage, we want this to assign a high value and say, you know, actually this value here does cause a lot of issues, and we want to identify those. And so the formula for leverage is, it's pretty complicated, so I won't really show it, but the idea here is that this formula will calculate a leverage statistic for every patient or for every subject, and the range will always be bounded between 1 over n, where n is the sample size, and all the way up to 1. And for the most part, the rule of thumb is a leverage value of greater than 0.2 is generally considered large. So if so let's go through the process again. So you run a regression, and you may call this your final regression, or you know, we'll talk about that with multiple linear regression. But let's say you have a final regression model. You say, I'm pretty happy with this. So what you do then is you go and you would interpret these coefficients, but then you would also say, what's my R squared, and then report that, and then you would say, well, let's go through and look at the assumptions of normality, homoscedasticity, linearity. You go through that process, and you see, well, there's maybe 1 or 2 data points that look problematic. Let me calculate leverage and then see if that value is greater than 0.2. Okay, so I'll show you how to do that. But if you see a value of greater than 0.2, that tells you that there's some observation, so some subject or a couple subjects that are really influencing the regression slope, and so you probably would have to consider some sort of sensitivity analysis just to make sure that it's not biasing it away from saying there is no effect, or the other way. So basically, just to make sure that your decision or that your interpretations are valid. Okay, so how do we do this in Stata? So again, let's let's consider this regression of child PPVT and mom PPVT. So you have this here, and again, assuming you had already gone through your residuals, your histograms, everything looks good, you're concerned about that one observation there, right? So let's go back to this figure here. So let's say you ignore this here, right? So this value here, it's within the bulk of y. Let's look at that. It's within the bulk of y, and it's outside the bulk of x. So this can be problematic. And if you can see this here, right, so imagine just ignoring this data point and then just looking at this scatter plot. To me, this seems like maybe the line should be somewhere around here. So maybe there's a stronger effect, right? So maybe the effect isn't 0.35, it could be more than that. And so how do we determine if this is a very influential data point? Is to look at leverage. And so on the slides here, I have the predict command. So we're going to use predict, and again, I'm calling this HI. You can call this whatever you want. You can call it leverage if you want, but I'm going to call it HI. And if you type in hat, that tells Stata to calculate these leverage points. And so let's look at the data browser. And again, so this row 1 is for subject 1, mom age 28, blah, 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 blah. Go to the end here. You've just created, when you hit the predict command, you've created a new variable called HI, and then it produced these values here, which tells you again, so for every subject, it calculates this leverage point and to measure how influential it is to these regression parameters. And so for this first person, it's 0.003. And if you go back here, again, the rule of thumb is a leverage of value of 0.2 is considered large. And so our goal here is then to look at to see which one of these has a value of 0.2 or more. I mean, so where I would start is I would say, well, let's look at the summary, right? So like summarize HI. So summarize HI will tell you, again, calculate summary statistics for this leverage column that I created, and it tells you what the average is, the standard deviation, which we don't really care much about that. What we care about is the maximum. So if I see a maximum that's greater than 0.2, then that's going to signal to me that I should go in and try to figure out which observations those are, and then remove them, and then rerun the analysis to make sure that everything looks good. And so this is one way to do this. So one way is to just summarize and then look at that. Another way is a command that Stata has, which is called the LVR2 plot, which I believe is in the slides here. So this is a built-in function in Stata that what it does is it calculates a couple things. So it calculates the leverage, and it also and it plots it against something called the normalized residual square. So this is how far the regression line and the data points are, right? So again, it's the residual squared. And so again, this gives you a sense of what the range is for leverage, anywhere from 0 to 0.08. That's so again, if I saw this and it went from 0 to 0.2 and there were values, there were any values above 0.2, then that would be problematic. And so one of the reasons why I like this plot is it does give you a little bit of sense of where these things are, and if you do see 0.2 or more and there's a data point anywhere that's above that, it's a really nice way to visualize that data set. But it also, if you type in LVR2 plot, comma, ML, and then ID. So I have in this data set I have in this data set a column called ID that is a unique patient ID for everybody. And so if I type in ML ID, you can see what this does here. So basically, for every data point, it attaches the subject's ID. Um, and so let's just say, for example, that this was 0.2 here. And if I saw a value here, I know exactly what that observation is, and then I can say, well, I'm going to do a sensitivity analysis removing this person. Okay, here again, because everything is below 0.2, I'm not too concerned, and I would likely just keep it, this regression analysis, as is. But for the sake of practice, so let's just assume that this subject ID 123202 had a high leverage above 0.2. So what I would do, and if you actually look at the data, this is that one data point that was causing issue, that was all the way to the left in the scatter plot. So let's just say we remove this subject there. How do we do that? So one way is to say drop if ID equals 123202. Okay, so if I want to do a sensitivity analysis, I could say I'm going to drop if the ID is equal to that, and so this will drop one subject. So one observation was deleted, and then I could rerun my regression here. So let's regress child mom PPVT, and so let's compare. So again, before we had 330 subjects, and I removed one because they were a potential outlier. In reality, the leverage was pretty small, so I wouldn't delete them in real life. But let's just say that it was large. Then we would go and rerun this analysis, and so the number of observations now we went down by one because we removed our potential outlier. And what happens to the coefficient here? So before the coefficient beta, the slope was 0.35. So we said for a 1 unit increase in mother's intelligence, child's intelligence went up by about 0.35 points. And in this new regression, it's about 0.365. So we did see the slope increase a bit. And if you wanted to get a new graph, you do again, you run the graph two-way, LFIT, and scatter. And you see that the observation that was all the way to the left, the potential outlier, is removed, and you do see a stronger line here. Okay? So, it doesn't necessarily always happen this way. Sometimes if you have an outlier, it actually could reduce your slope, as we were looking at this here, right? So this, if you had a slope like this, and if you're looking at an outlier like C, this slope could go down here. So you may actually have that issue, or you may have a different type of issue. But always double check. Always make sure that you look at the leverage. You look at all your model diagnostics, because you may have an issue like this. And so I guess just to sort of recap this little bit of discussion on outliers, I guess the next question would be, so what do you do in practice? So let's say that there was a leverage point or two or three that were above 0.2. What do you do in practice? And so in practice, what I would say is you do the sensitivity analysis. You remove those points and you rerun your analysis. And if things don't dramatically change, I would say keep the original data and just report that you did a sensitivity analysis and everything looked good. Now, if things do change, I think that's a sort of a harder decision to make. So what do you do? Do you report? If things become significant or if things become non-significant, so which do you do? Which do you report? And I would say you report both. I think at that point you just say, hey, we're going to report both of those, and then do as best you can to figure out if those outliers are real outliers, or if they're maybe it's a coding error, maybe it was a data entry error, and sort of go from there. Okay, so I think definitely write down any questions that you may have, and we can discuss them when we meet in person. But this is sort of the last bit of model diagnostics for simple linear regression that we will discuss. So let's go back to the slides here. Okay, I'm gonna stop this video here and then start part 2 starting from gender.